Surimi comes from Japanese term which is used for minced fish flesh obtained after processing steps. Frozen surimi product was made by mincing fish flesh which gone through washing with water, draining the water, mixing carefully with sugar and polyphosphates, and lastly freezing. Alaska pollock is mostly the main ingredients of frozen surimi. In Japan, kamaboko, nerisehin, chikuwa, hanpen, kanibo, kanikama, naruto, satsumeji, shi surimi are the fish gel product which has been extensively used. Marine organisms which has been made into product were consumed in different ways since the old time. Food industry has been developed that produce the standardization in seafood. Surimi is a unique product as it has been produced from different ways and in fact it is a Japanese term for kneaded fish flesh. 400 years ago, kamaboko was produced by original method that involved dough cooked from salted fish meat. Basically, the production of kamaboko back then was just to bake the fish means produced from fillet, which began by washing with fresh water first and followed by salted water, then shaped on a piece of wood. Hence, kamaboko is a general term used for all surimi products. However, today surimi covers a range of different products. Basically, after mechanical removal of bones from fish flesh and removal of fat, free amino acids and peptides from the remaining meat by washing, which is followed by adding different additives, surimi was produced and described as the concentration of myofibrillar proteins. Washing is an essential step to remove sarcoplasmic proteins. When sarcoplasmic proteins were removed, it concentrates myofibrillar proteins, which is the primary component in the formation of three-dimensional gel structure. Removal sarcoplasmic proteins is responsible for the gel-forming ability of surimi. The number of washing cycles and the volume of water depends on fish species, freshness of the fish, type of washing unit, and the wanted quality of the surimi.
Surimi is a product prepared from either deboned meat or fillets. It consists mainly of muscle protein fibers that have been washed several times. Surimi is also prepared by mechanical deboning, but it reduced essentially to muscle protein fibers by repeated washing. Some studies has reported that the microflora on surimi is similar to the microflora of fresh fish and consists of Moraxella, Pseudomonas and Corynebacterium. Bacteria grow well in surimi and surimi-based product. However, these are the mostly stored frozen. Hence, bacteria grow is not a problem. Microbial spoilage involve growth of bacteria, yeast or fungi to the high numbers and products of their metabolism give rise to the sensory impression perceived as spoilage. Visible slime may appear as a result of the formation extracellular polysaccharide from carbohydrates. Typical spoilage compound of seafood products include ammonia from the amination of amino acids, sulfide formed from sulfur-containing amino acid, trimethylamine resulting from bacterial reduction of trimethylamine oxide, and esters that may arise from degradation of phospholipids. Often these products are microbiologically stable. However, when spoilage occurs, it is typically due to the growth of acetic acid tolerant lactic acid bacteria of yeast. Spoilage can be characterized by gas formation produced by heterofermentative lactobacilli such as Lactobacillus alimentarius. Spoilage may also be manifest by slime or roughness, which is caused by the growth of leuconostoc species or halophilic gram-negative root-shaped bacteria. Prevention and retardation of food spoilage. The first one is low temperature storage. Low temperature storage has been the method of preservation used to retard microbial spoilage of a wide range of seafood since the mid-19th century. It prevents spoilage or contaminating microorganisms from metabolizing, growing, and causing spoilage without necessarily killing them. The refrigeration process usually results in an initial reduction in the microbial population followed by a gradual decline during storage, with the survival of spoilage microorganisms during the storage period being dependent on the types of microorganisms and fish species, history of the fish, method of catch, and the handling of storage process aboard the fishing vessels. Refrigeration has the advantage of maintaining freshness and overall organoleptic quality of fish products, but its inability to kill or completely eliminate microorganisms poses potential health risks. This is particularly true when one considers that proper refrigeration probably will not be maintained at some point during distribution, storage, display, or consumer handling. Second one is chemical treatments. No matter how effective a storage technique may be theoretically, A heavily contaminated or poor quality product will eventually reduce the shelf life under the condition of storage. Good initial handling techniques are therefore critical to reduce microbial loads. To accomplish this, high pressure washing of the whole fish may be applied to remove surface slime and it is associated microflora. Studies by Statham have shown that the combined use of sorbates and polyphosphates prior to storage improve the shelf life even further. The polyphosphate enhance the preservative role by acting as metal ion chelators, acting as pH buffers, interacting with proteins to promote hydration and water binding capacity, and preventing lipid oxidation and inhibiting microbial growth. When the metal ions are chelated, the structural integrity of the cell wall is compromised, resulting in increased permeability of the cell wall to compounds capable of interfering with the growth. Examples of polyphosphate used to date include sodium tripolyphosphate, disodium orthophosphate, tetrasodium pyrophosphate, and hexametaphosphate. Ethyl enediamine tetrahexate has also applied as a chelating agent in fish processing in combination with other treatments. The third one is low-dose irradiation. Food irradiation involves the exposure of food products to ionizing radiation to improve the shelf life or wholesomeness of the product as a result of the antimicrobial effects of ionizing radiation. The antimicrobial effect is due to damage of microbial DNA, resulting in an interference with normal biochemical process. Since the mid-1950s, the technique has been shown to maintain the quality of freshness of seafoods, with the gram-negative spoilage bacteria being more sensitive than the gram-positive species to low-dose irradiation. Of critical importance in the application of irradiation to control microorganisms in seafoods is the time of exposure and irradiation dose, as microorganisms respond differently depending on their specific cellular characteristics.
The food composition of Surimi product is Alaska Pollard Surimi 52.78%, potato starch 2.64%, wheat starch 2.64%, sugar 1.4%, salt 1.29%, crab extract 1.17%, carrageenan 0.59%, cape extract 0.4%, albumin 0.41%, calcium carbonate 0.66%, crab flavor 0.29%, soybean oil 0.33%, mixture seasoning 0.29%, phosphate 0.2%, red coloring 0.03%, flavoring 1.88%, and the last one is distilled water 33%.
When the fish are caught in large nets, they must be manually sorted by species and cleaned. They are further mechanically sorted by size to optimize the yield of fillets. Scales are mostly removed from the fish after sorting. The fish are then converted to a filleting machine which removes the head, tail, and viscera. Water washing is done next to remove the excess fluid. The prepared fish fillets can then be minced or mechanically deboned and made into surimi. This is done using a mechanical deboner which removes the skin, scales, fins, and bones. The minced fish is next thoroughly washed with water in process called leaching. Leaching removes many undesirable water-soluble materials such as fats, unorganic salts, and some proteins. After the final leaching cycle, the mince is partially dewatered. After dewatering, the surimi flakes are then mixed. together in a stone bowl grinder with other ingredients in the crab meat recipe. These ingredients include starch, salt, natural crab meat, egg white, flavoring, and cryptoprotective compounds. Imitation crab meat is mechanically vacuum packed in thermoform trays. This protects the meat from contamination and provides an appealing look. After packing, the imitation crab meat is typically pasteurized in a steam cooker. This step helps prevent bacterial growth and increase shelf life. The surimi is stored below -4 Fahrenheit until it's ready to be used.
The processing of surimi. The first step is fresh whole fish normally received in insulated vehicle is unloaded and taken into raw material receiving room through queue door. The organoleptic inspection, which is aspect of food, water or other substance that an individual experience via the senses including taste, sight, smell and touch. And temperature check of the raw material is carried out, and if found unacceptable is rejected back to the suppliers. Fish is drained and weighed. Raw material is iced properly and if necessary stored in the chill room 2 to 5 degrees Celsius properly iced. So the second step is feeding and gutting. Mechanical fish meat separator developed by companies in Japan, Germany and United States. A modern sanitary machine that removes virtually all the flesh from the frame of properly prepared fish. There are several methods to prepare fish for deboning. One is to remove the head, gut and thoroughly cut the belly walls before deboning the fillet, which also contains skin debone. So the third step is meat separation, which is mincing. Debone fillet give cleaner minced meat because blood, membranes and other contaminants have been removed. A beheaded and gutted carcass, on the other hand, result in higher final yield of minced flesh, but the quality is relatively low. Another method is skin on fillet, which is butterfly shape, which increase yield and keeps quality low to minimum. So the fourth step in the surimi processing was washing. The most important step of surimi processing to ensure maximum grilling as well as colorless and odorless surimi is efficient washing. Many of the problem with color, taste and odor that develop in mince is minimized or eliminated when washed. The number of washing cycle and volumes of water varies with fish species, freshness of fish, type of washing unit and desired quality of the surimi. The fifth step of surimi processing is the watering. The moisture content of refined mince is about 90%. In order to reduce moisture content to about 80 to 84%, final dewatering is carried out in a screw press consisting of a rotary screw and cylindrical screen. So the sixth step of processing surimi was by adding several types of additive to the fish, for example cryoprotectant, which is important to ensure maximum functionality of frozen surimi because freezing induces protein penetration and aggregation. There are other additives that commonly was added to the surimi such as egg white and that improve the texture, vegetable oil that improve the appearance of surimi, flavoring and seasoning to make it taste better and like a crab meat, and coloring to get appearance of surimi looks like crab meat. The seventh step of processing was forming into the crab meat. The blended material is shaped normally into either cuboid or cylindrical shape with appropriate size by using a machine. So the 8th step was packaging. Surimi crab stick are normally used material that can resistance to very high and low temperature, such as low density polyethylene, which is LDPE. The plastic will cover for the edge of stick to maintain the shape. The secondary packaging was vacuum packaging. The last step, which is cold storage. After the pasteurization, the package will be shifted to cold storage which is maintained below -18 degrees Celsius. The purpose of the cold storage is to hibernate the growing of microorganisms. For the pasteurization step, after the crab stick was packaged, they will pasteurize by using water bath at 91 degrees Celsius for 25 minutes to achieve an internal temperature of 81 to 85 Celsius for at least 5 minutes. So the preservation of surimi can be done by lowering the water activity. It has been reported that had the greatest effect on lowering water activity with the efficiency of the reduction in water activity value, decreasing in order of sodium chloride, sodium lactate glycerin, propylene, glycol and sorbitol when each of them was combined with the other humectants. Second, preservation of surimi can be done by salt. Salt had in protein-protein interaction, and the addition of salt is critical during processing of fish-based product. Besides that, salting used because most bacteria, fungi and other pathogenic organisms cannot survive in highly salt environment due to the hypotonic nature of the salt.
Various ingredients are added together to make the product has the color, taste and texture of a crab meat. Crude protecting materials such as sugar and sorbitol are added to prevent the degradation of the gel-forming properties and help to extend its shelf life. Starch was added to improve the texture and stabilize the gel strength and making the surimi glossy and whiter. Vegetable oil is also used to improve the appearance of surimi and modify its texture. Flavoring such as amino acid, proteins and organic acid which are obtained through aqueous extraction of edible crab is added to surimi to make it taste like a crab meat. Additionally, seasoning and secondary flavoring such as nucleotides, monosodium glutamate, vegetable proteins and mirin are added to the meat to improve the overall flavor. The coloring such as carmine, caramel, paprika and annatto combining and other ingredients various shades of red, orange and pink can be obtained to look closely like a crab flesh.